Well, welcome back to our course on system engineering. In this chapter, in this lecture, we're going to be talking about operation and support. And just to give you the context where we are in the overall class, we've talked about foundations, which is a nice overview of what system engineering is all about. One or two chapters were fairly involved in that. We then talked about concept development, the things that are done at the front end of a program development. We then got into the details of what happens when you actually do the engineering development, the hands-on building hardware. And now we're in this post-development stage where we're in production. And now for this lecture, we're going to be talking about the operation and support. So first of all, let's get into the installation, maintenance, and upgrading of the system, how that's approached. The operating and support phase of the system lifecycle is a time during which the product of the system development and production phases perform the operational functions for which they were designed. In theory, the task of systems engineering have been completed. In practice, however, the operation of modern complex systems is never without incident. Such systems usually require substantial technical effort in their initial installation and can be expected to undergo significant testing and component replacement during periodic maintenance periods. Occasional operational glitches must also be expected due to operator error, operating stresses, or random equipment failures. In some cases, systems engineering principles must be applied by system operators, maintenance staff, or outside engineering support to identify the cause of the problem and devise an effective remedy. Further, large complex systems such as air traffic control systems are too costly to replace in their entirety and therefore are subject to major upgrades as they age, which produce new subsystems in place of obsolescent ones. All of these factors are sufficiently significant in the total role of system engineering in the overall system lifecycle to warrant a special place in the study of system engineering. The principal sections, what we're going to talk about here in this lecture and the corresponding chapter, that take place in the course of the system operating life begin with the time it is delivered from the production or integration facility to the operational site until it is replaced by a newer system or otherwise rendered obsolete and disposed of. So in the installation and test section, it deals with problems associated with integrating the system with its operating site and the successful interconnection of internal and external interfaces. In the section dealing with in-service support, it's concerned with activities during the normal operation of the system. These include maintenance, field service support, logistics, and dealing with unexpected operational emergencies. For the section dealing with major system upgrades, looking at modernization, it is concerned with the periodic subsystem modifications that may be introduced to maintain system effectiveness in the face of changing user requirements and advancing technology. Such system upgrades require the same type of system engineering expertise as did the original system development. It may also present new and unique challenges due to added constraints that may be imposed by the process of integrating new and old components. For the last section, dealing with operational factors and system development, describes the kind of information that systems engineers should seek to acquire regarding the operational characteristics of the system being developed, together with the opportunities that they may have for obtaining such knowledge. Such knowledge is just as important to system engineers who lead the system development as is a firm grounding in factors that affect system production processes and cost. Okay, well, let's think about the place of the operation and system support phase in the system lifecycle. So before discussing the system engineering activities during the operation and support phase, it should be noted that the phase is the concluding step in the system life cycle. The functional flow diagram that we're showing here shows the input from the production phase to be operational documentation and the delivered system, and the output to an obsolete system and a plan for disposing of it in an appropriate way. So in terms of the system engineering in the operating and support phase, we're getting a chance to be looking here at the system operating history. So during its operating life, a typical complex system encounters a number of different periods when its operation is interrupted. And so we're showing that here. And so the abscissa is time running from system delivery to disposal. With the ordinate, the y-axis represents the relative level of system engineering involvement in the various events that identified by the captions in the upper part of the figure. As in at the start, it is seen a column symbolizing the installation and test period, which is shown to take substantial time and a relatively large systems engineering effort. The four lower regularly spaced columns represent planned maintenance periods, which may require days of system downtime. The narrow spikes or irregular events are meant to correspond to random system breakdowns requiring emergency fault identification and repairs. These are usually fixed quickly, but may take considerable system engineering effort to find a solution that can be affected with minimal downtime. The large column on the right represents a major system upgrade requiring a relatively long period and a high level of system engineering. The latter may rival the effort involved in a new system development, may itself require a multi-phase approach. Okay, well, let's get into installation and test. And so there's a lot of material to cover here. So some of it I'll just give an executive summary, and there'll be some more details that you can refer to in the textbook. So for system installation, the effort required for installing a delivered system at its operating site is strongly dependent on two factors. One, the degree of physical and functional interaction that it had been accomplished at the production facility, and two, the number and complexity of the interfaces between the system and the operating site. In the case of an aircraft, for example, virtually all significant system elements typically are assembled and interconnected at the primary contractor's facility site, so that when the aircraft leaves their production facility, is ready for flight. The same is true for an automobile, a military truck, or almost all kinds of vehicles. The installation of many large-scale systems on a land or ship platform may be a major operation, especially if some of the subsystems are manufactured at separate location by different contractors and assembled only after delivery to the operating site. So the textbook walks through some examples of that you can feel free to spend some time reviewing in more detail. For the internal system interfaces, as we discussed previously, the system engineer has a responsibility to ensure that the system integrity is maintained throughout assembly and installation. Installation procedures must be carefully planned and agreed to by all involved organizations. The system engineer must be a key participant in the planning effort in seeing it properly carried out. However, regardless of the degree of planning, the proper integration of subsystem interfaces will always be a potential source of trouble and therefore deserve special effort. So there's more details on that you can feel free to get a chance to look over in more detail. For the system integration site, for systems where integration of major subsystems is especially difficult to accomplish at the operational site, it becomes cost-effective to utilize a specially equipped and supported integration site where subsystems and components are assembled and various levels of checkout are performed prior to partial disassembly and shipment to the operational site. This may be the same integration site that is used during development to test and evaluate various elements of the prototype system, or it may be a separate facility also used for training of operations and maintenance personnel. Then for the external system interfaces, in addition to numerous internal subsystem interfaces, complex systems have many critical external interfaces. Two examples are prime power, which is usually generated and distributed by an external system, and communication links, which interface through hardwired electronic circuits or by microwave links. So communication links not only have to be electronically compatible, but also have the appropriate set of message protocols, which are usually processed by software. Further complicating factor is a large system must often interface with systems that are procured from developers who are not under the control of either the prime system contractor or the system acquisition agent. So there's some more issues that need to be worked out on these fronts, and that's something that system engineering is going to have to be involved with. So there's more details in the textbook, but that gives you a good introduction to the flavor of what needs to be thought about for that. Well, now let's talk about non-disruptive installation. Some critical systems require continuous operation, cannot be stopped or paused during system installation or upgrades. This tends to be the case when installing a system into a large system of systems or systems of systems. The installation of new or upgraded systems into the system of system cannot disrupt current operations. So there's a variety of different examples on a city power grid, a complex industrial wide area network, a national communication network, a major defense system, the national air traffic control systems are all examples of things that would fall into that area. So what we're trying to show in this figure is a depiction of how this could actually take place, a non-disruptive installation by simulation. So now you can see that things are working, and then you could actually do the installation. With this strategy, a system of system simulation with hardware in the loop is created. The simulation is typically user in the loop as well, as opposed to standalone. The simulation facility is verified and validated against actual data collected from the operational system of system, which interacts with the environment. Typically, the simulation would not interact with the environment. So there are, once again, more details that you can read in the textbook that gives you some more perspectives on how this could be done. And so here is another alternative, non-disruptive installation via a duplicate. The second concept used within non-destructive installation involves the development of a duplicate system of systems scaled down from the operational one and is depicted here in the figure. The concept is similar to the first concept, and the system is installed into the scaled down version of the system of systems, and testing occurs. During this process, the duplicate system of system is typically disconnected from the operational system of systems to avoid any interference or disruption. An installation strategy is developed from the experience to apply for installation to a full-scale system of systems. So there's more details that you can look at for that. And there's a few other concepts related to this that we want to just quickly cover. In terms of facilities and personnel limitations, neither the facilities nor the personnel assigned to the task of system installation and test are normally equipped to deal with significant difficulties. Funds are inevitably budgeted on the assumption of success, and while the installation staff may be experienced in the installation and test of similar equipment, there are seldom knowledgeable about the particular system being installed until they have gained experience during the installation of several production systems. So this is something that system engineering can be a useful player for trying to bridge that gap. And then for early system operational difficulties, many newly developed pieces of equipment, new systems are composed of a combination of new and modified components and are therefore subject to excessive rates of component failure or other operational problems during the initial period of operation, a problem that is sometimes referred to as infant mortality. This is simply the result of the difficulty of finding all of the system faults prior to total system operations. So that's just another factor that is useful to be mindful that that's something that could potentially come up. And you can go to the textbook for more details to read up on that further. Next, let's talk about in-service support. First of all, operational readiness testing. Systems that do not operate continuously, but that must be ready at any time to perform what is called upon are usually subjected to periodic checks during their standby periods to ensure that they are operated at their full capacity when required. An aircraft that has been idle for days or weeks is put through a series of test procedures before being released to fly, as an example. Most complex systems are subject to such periodic readiness tests to ensure their availability. Usually readiness tests are designed to exercise, but not fully stress, all functions that are vital to the basic operation of the system or to operational safety. So these periodic tests also provide an opportunity to collect data on the history of the system operating status throughout its life cycle. So what are some of the commonly encountered operational problems? You could have a system fault. Faults in the system, complex software-intensive systems are notoriously difficult to eliminate and tend to persist well past the initial system shakedown period. That's something that needs to be monitored and explored. There could also be complex interfaces during system installation. We note that external systems interfaces are always a potential source of problem. During installation, there is always a strong push for accomplishing the process as quickly as possible so that operational schedules are maintained. So once again, these interfaces can show up to be an issue, and so that's good to be aware of. In terms of field service support, it is common for deployed complex systems to require field support during the lifetime of the system. In the case of military system, this is often provided by an engineering support unit within a branch of the service. It is also common that the unit to contract with civilian agencies to provide general engineering support to keep these systems operational as intended. So that's yet another one that needs to be monitored as things go. There's also scheduled maintenance and field changes. Most complex systems undergo periods of scheduled maintenance, testing, and often revalidation. Non-emergency field changes are best accomplished during such scheduled maintenance periods when they can be carried out under controlled conditions by expert personnel and can be properly tested and documented. There's also the possibility for severe operational casualties. And so what we discussed earlier, and also what's in the textbook for more details on dealt with operational problems that could be corrected during operations or short periods of scheduled maintenance. Must be assumed that a complex system built to operate for a dozen years or more may accidentally suffer a failure of such magnitude that it's effectively put out of commission until corrected. And so that's yet another potentiality that needs to be thought about. Finally, for logistics support, the materials and processes involved in the logistics support of a major operational system constitute a complex system themselves. The logistics for major fielded systems may consist of a chain of stations extending from the factory to the operational sites that supplies a flow of spare parts, repair kits, documentation, and when necessary, expert assistance as required to maintain the operational readiness of at all times. So see the textbooks for more details on that. Well, what about when we have a situation where there needs to be modernization? So there's a major system upgrade And we saw this in the beginning of the chapter where we saw a timeline. You can see that there was a larger upgrade that was included. So in the previous lectures and chapters that dealing with the origin of new system, it was noted that systems are usually developed in response to the forces of advancing technology and competition, which combine to create technical opportunities and generate new needs. Similarly, during the development and operational life of a system, the dynamic influence of these same factors continues. All of that is true, can be advances in technology that are far from uniform across the many components, and so that's something that would need to be explored. Thus, obsolescence of a large complex system often tends to be localized to a limited number of components or subsystems for and the ones that are getting into the front end of technology and so those would be things that we'll be focused on. Well, skipping ahead for other things, for system upgrade life cycle, the development, production, and installation of a major system upgrade can be considered to have a mini life cycle of its own with phases that are similar to those of the main life cycle. So as you see the details of this, you get exposed to that in the future, you'll see those commonalities. For the conceptual development stage, like the beginning of a new system development, the upgrade life cycle begins with the recognition through a needs analysis process of the need for a major improvement in mission effectiveness because of growth in mission needs and deficiencies in the current system's response to those needs. There follows a process of concept exploration, comparing options, several options of upgrading a portion of the current system with a total replacement by a new and superior system, as well as the options for achieving the objective by different means. So you're going to be doing various trades. There's going to be the concept development phase, which we've already spoken about, until you finally get to a point where a decision is made that this is what you want to be working on and what's going to be deployed. Then we get into the engineering development phase, the advanced development phase of the upgrade program. And most of the engineering design phase is limited to the new components that are to be introduced. So once again, we're not necessarily doing everything, but the things that are part of this modernization upgrade. There's also the system test and evaluation. The level and scope of system test and evaluation required after a major system upgrade can range all the way from evaluating only the new capability provided by the upgrade to a repeat of the original system evaluation effort. So that's going to be something that would have to be worked with the customer in understanding the magnitude of what the modernization might do to the overall performance and what needs to be validated. Like before, we have operation and support. Major upgrades always require corresponding large changes in the logistic support system. Maybe different parts that need to be made available, operational training with accompanying manuals and system documentation that must also be provided. There could be software upgrades. And so as described in some previous material, software is much easier to change than hardware. Such changes usually do not require an extensive system stand down or special facilities. And so that would be something that's true, but you also have to make sure that you validate that the software as a whole is functional. And so there's more details in the textbook that you can read to get some more insight on that. We also have pre-planned product improvements. And so for systems that are likely to require one or more major upgrades, this strategy referred to as a pre-planned product improvement, P3I, is often employed. The strategy calls for the definition during system development of a planned program of future upgrades that will incorporate a specified set of advanced features, thereby increasing system capabilities in particular ways. So that's a quick synopsis of what goes on for a major system upgrades modernization. There's, like I said before, there's more details in the textbook that you can look over in more detail. Well, what about the operational factors in system development? And so in some previous things that we've covered in this course and previous chapters, it was pointed out that system engineers who guide the development of a new system must have significant firsthand knowledge of relevant production processes, limitations, and typical problems in order to coordinate the introduction of producibility considerations into the system design process. It is likewise important that system engineers be knowledgeable about the system's operational functions and environment, including its integration with the users, in order to be aware of how the system design can best meet the user's needs and accommodate the full range of conditions under which the system is to be used. So unfortunately, the kinds of opportunities that exist for system engineers in a developer organization to learn about manufacturing process frequently are not available. And so that's something that needs to be dealt with, but you could have a tour where you're involved in that. And so consider that as maybe something that you might want to be considering. So the term operational environment as used here includes not only the external physical and conditions under which a system operates, but also under factors such as characteristics of a system interfaces, procedures for achieving various levels of system operational readiness, factors affecting human-machine interfaces, human-machine operations, maintenance, and logistic issues, and so on. More details in the textbook, or you can spend more time going over that. What about the sources of operational knowledge? A number of potential sources of operational knowledge may be available in certain situations. These include operational tests of similar systems, integration tests during system installation, system readiness test, and maintenance operations. Since these address the problems associated with successfully integrating the system's external interfaces with the site and with associated external systems, these often can often expose serious problems that are not adequately revealed by the interface specification provided to the developer. So those are things to consider. There's also the system readiness test. A useful source of operational knowledge is observable processes used to determine the level of system readiness. All complex systems go through some form of checklist or fast test sequence prior to operation, often using automatic test equipment under operator control. Also, the operating modes are something that will be explored. Most complex systems include a number of operating modes in order to respond effectively to differences in their environment or operating status. Some systems that must operate in a variety of external conditions, such as a military air defense system, usually have several levels of operational readiness. For example, threat possible, threat likely, full-scale hostilities, and periods of scheduled maintenance or standby. Finally, for assistance from operational personnel, view of the limited opportunities for developing system engineers to acquire an adequate level of operational experience, is it often advisable to obtain the active participation of experienced operational personnel during system development. They can be helping to give that perspective that may be lacking, since there's not as many opportunities for system engineers to get that kind of experience. All right, well, let's finish up with this chapter. So we'll do this summary review. So there's 5 things that we focused on. First of all, installing, maintaining, and upgrading the system. Application of system engineering principles and expertise continue to be required throughout the operational life of the system. The operations and support phase includes installation and test, in-service support, and implementation of major system upgrades. Interface integration and test can be challenging due to a mixture of various organizational units, complex external interfaces, and incomplete or poorly defined interfaces. For installation and test problems can be difficult to solve because installation staff have limited systems knowledge. System engineers are seldom assigned until trouble is encountered. However, periodic operational readiness tests is necessary for systems that do not operate continuously. This can help minimize unexpected system problems. While non-disruptive installation is required, care to plan the installation procedures via hybrid simulation or a duplicate system operating in parallel is absolutely essential. In terms of in-service support, system software must be subject to strict configuration control to prevent serious deterioration of software quality. In this vein, built-in fault indicators are very valuable for detecting internal faults, although they sometimes produce false alarms. Therefore, field engineers should be knowledgeable about built-in test devices. Remedial actions to correct operational problems are difficult to implement. Operational personnel are not technical specialists. Furthermore, troubleshooting tools are limited, and materials and processes involved in the logistics to support themselves constitute a complex system. In terms of major system upgrades, modernization, logistic cost is a large part of system cost. Therefore, pre-planned product improvement facilitates improvement of systems during major upgrades. Advanced features are defined during system development, and advanced planning permits minimum disruption to system operation. And finally, operational factors in system development. Possible sources of operational knowledge includes operational and installation tests by observing system operations within its environment. Of course, assistance from operational and maintenance personnel is invaluable. Okay, that's going to end it for this lecture. Thank you very much.